Okay, so I consider this unit to be the most important unit in the entire course. What we saw earlier in this section is that if you know the loop invariant, then the entire loop is prescribed. The loop guard, the initialization, and the loop body can all be derived from knowing the precondition, the postcondition, and the loop invariant. So, how do we come up with loop invariants? How do we systematically derive them? If we can crack that, then we're done as far as loop-based algorithms are concerned. The fact is that when people pushed for goal-oriented programming, for loop-based algorithms, they got stuck in a hurry because how to derive loop invariants systematically for anything but trivial examples turned out to be difficult. Now, in this particular week, we only see very simple examples, and therefore you may walk away with thinking that this is all rather trivial. Not so. If you stick around for the rest of the class, you will find that we can apply the same techniques to rather complex dense linear algebra operations, and that's one of the contributions that our research group has made over the last 15 or 20 years. We figured out how to systematically come up with loop invariants for progressively more difficult operations in our domain. So let's have a look and see how we do this for problems that involve linear arrays, one-dimensional arrays. Okay, so we go back to our workhorse example of adding the elements of array X to the corresponding elements of array Y, and both arrays are of size n. And what do? Well, we specify the operation with the precondition and the postcondition. The precondition says that array Y contains its original values, where Y hat is this dummy variable, or array in this case, that we introduced to be able to reason about the original contents. And then the postcondition says that the array Y has been overwritten with the original contents plus the corresponding entries in array X. Now, when we write a loop over a one-dimensional array, we tend to systematically go through that array either from the first element to the last element or the last element to the first element, and therefore there is an index, let's call it k, that somehow tells us where in the arrays we are. So let's use that index k to split the range. Here we have taken the precondition and we've split it into two quantifiers. One that says the first k entries in the array equal the original contents, and the second one says and the remainder of the array also contains its original contents. And the box highlighted here in green is necessary to make sure that in the quantifications you only access entries that are actually part of the array. Okay, remember, these are arrays that are indexed from 0 to n-1 because there are n entries in the arrays. And that then tells us that k should be between 0 and n inclusive, because if you take 0 and plug it into the first quantifier, then you get the empty range. That's okay. And if you plug it into the right quantifier, then you only index I from 0 to n-1, and therefore evaluating the arrays for those I is valid. And that's how you reason through that. Similarly, we can partition the postcondition. There, the left quantifier now says that the first k entries contain the updated values, and the right quantifier says and the rest of the entries also contain the updated values. And again, what's in the green box just limits k so that you only address entries in the arrays that are valid entries, indexed from 0 to n-1. So, a loop invariant captures partial progress towards the final result. Where does that come from? Well, notice that if the loop is still executing, then inherently you aren't done yet, but hopefully you have done useful computation so far. So what you've computed so far is a partial computation towards the final result. And partial we take kind of loosely here. If you haven't done anything yet, we will call that partial progress. And if you have completely finished, that actually is partial progress too. There just happens to be no computation left to be done. So what that tells us is that we should look for taking pieces from the partitioned precondition and the partitioned postcondition and see if we can't kludge those together into something that can become a loop invariant. And what have we done here? Well, candidate A, so these are candidate loop invariants that we're going to discuss. Candidate A says that the first k entries are the original contents and the last k entries are the original contents. Probably not a very interesting loop invariant. Candidate B says that the first k entries have been updated with the final result. That sounds like progress. And the rest of the entries have not yet been updated. That seems like a reasonable loop invariant. Candidate C says that the first k entries have not yet been updated, but the rest of the entries have been updated. Again, that seems like the kind of thing that represents partial progress. And then the final candidate, D, says that all entries have already been updated. The first k entries have been updated and the remainder of the entries have been updated. That's probably not a particularly interesting loop invariant either, because as you execute the loop, everything is already done. So, what is going on here? Well, let's for the fun of it go and look at candidate A. And let's go ahead and plug that into our worksheet and look at everywhere where this loop invariant must be true. Now, importantly, the loop invariant must be true after the loop is done. And notice that we have to come up with some loop guard G such that G not being true implies that we've computed the final result. But notice that there is no way of picking a loop guard G in such a way that the loop invariant, which says that nothing has been computed yet, implies that we're done. So the fundamental problem with candidate loop invariant A is that you can't find a loop guard such that completion of the loop implies that you've computed the correct result. Therefore, this is not a valid loop invariant. Okay. You can also go to the top and say, well, what if we pick candidate D? Candidate D was that the first k entries have already been updated and the remainder of the entries have been updated as well. Well, notice that there's no initialization short of actually going and computing everything that will put you in a state where the loop invariant is true. So here we can't find a simple initialization that actually puts us in a state where the loop invariant is true. And therefore that is not a valid loop invariant either. And that then leaves us with two loop invariants from which we can actually derive a proper loop. There's another way of looking at this. Look at the postcondition R. This is what you want to compute. Split the postcondition into a part that says something about the first k elements of array Y in this case, and then the remainder. Okay, and again, the green box there has to be introduced to make sure that in the quantifiers you don't address entries in arrays X and Y that don't exist, that are not between 0 and n-1 inclusive. Okay. Now, what constitutes a partial result? A partial result can be created by saying that the first k entries have been updated, but not the rest of the entries. Notice that what's in orange here now constitutes the original values in Y and therefore is part of the precondition. Or you can say that the first k entries have been left alone and the rest of the entries have been updated. And both of these constitute a partial result towards the final result. So what do we see here? You look at the postcondition, which tells you everything that needs to be computed. You split its range because from experience we know that we tend to march through one-dimensional arrays in a systematic manner. And you then look at those two quantifiers that pop out, and then you say modify them so that they represent a partial result towards the final result, and bingo, what you have is a loop invariant. So in summary again, the loop invariant represents a partial result towards the final result, which is given by the postcondition, and therefore there should be a systematic way of deriving loop invariants from the postcondition, keeping in mind what the precondition is.